Hi, I'm Anup Shakya. I'm a PhD student at the University of Memphis, and this is my presentation on mastery-guided non-parametric clustering to scale up strategy prediction. So first, with the background. So different students have different learning capabilities, and being able to address each student's learning capabilities is very vital to understanding at a deeper level how students learn and how they think. So students' learning is affected by different experiences that they have during their learning period. So being able to personalize instructions to the students based on their needs is very important. So one way to learn about the way students think about problems is analyzing their mastery over different concepts. Mastery and the selection of strategy is very related. The strategy that the student use also indicate the level of sophistication of their mastery over the different concepts. Now, humans can identify the strategies used by the students and provide the relevant instructions easily. However, it becomes very tricky for big education data where there are millions of interactions between the students and tutors. Therefore, if we exploit the relation between strategy and mastery to compute the symmetries between students' problems and their strategies, then we can better scale up learning from such big education data. So the problem that we are trying to tackle in this paper is given a student S and a problem P, we are to predict the sequence of knowledge components or the strategy that the student might use to solve the problem. Here we consider the strategy as a discrete sequence of steps used to solve the problem. So we define the strategy as follows. So given a student S and a problem P, we define the strategy as the sequence of knowledge components that the student uses to solve the ith discrete step in the problem. Here, the sequence of knowledge components from 1 through 7 is the strategy. The dataset that we use is a real-world dataset collected from Mathia. Mathia is an online math tutor used in different schools for the middle school students. And both of these two datasets used here are huge datasets. They contain structured interactions between a computer tutor and the students, where the students are solving algebra problems. There are about 1.9 million such instances of interactions for about 6,000 students. This is a snippet of the dataset where each row records a transaction between the student and the tutor. So the proposed solution in this paper is we encode the symmetries over mastery and use this to learn a vector representation. Then we use mastery to guide us to divide the students and problems into partitions. Such partitions will represent the similarity of mastery in the students. And once we get those partitions, we simply sample from those partitions to pick up the most diverse strategies that we use to train our strategy prediction model that helps us scaling up learning from big education data. So more on the mastery embeddings. So mastery in a skill or a concept implies that the student is able to apply the skill correctly in the correct context when they have an opportunity to apply it. For example, if a student has mastered the skill of addition, then they will be able to use it correctly, either it's for solving equations or for solving word problems. So mastery and strategy are very related. So we train an attention model to quantify this mastery over a knowledge component. Then we use this to learn a representation that we call mastery vector representation, or MVEC. To train the MVEC, we use a very similar approach to node-to-vec. So for this, we first represent the student problem and knowledge component network as a relation graph Z. Then we sample paths from this graph and learn embeddings for those paths using word-to-vec. So there are different strategies for sampling the paths from this graph. One way is random sampling. However, for our purpose, we used to quantify mastery over cases as the sampling probabilities while generating the walk. So more on this on the paper. So our goal here is to divide the students and problems into clusters such that the strategies in those clusters are invariant. So once we have this, we can simply sample from those clusters and we'll be able to pick up the most diverse strategies. But we do not know in advance like how many clusters are there. So for this, we use non-parametric clustering, and specifically we use the hierarchical Dirichlet process framework, which has a penalty parameter lambda that controls the number of clusters that are formed. So we perform coarse-to-fine refinement, where if we start with a large value of lambda that results in a lower number of clusters, we slowly refine those clusters and get more finer clusters and sample from those clusters. So more details in the paper. So the machine learning models that we use, the first one is the transformer-based model that we use for mastery quantification. And these are the parameters that we use for the model. The second one is the LSTM-based model, that is one-to-many LSTM model. We use it for strategy prediction. And these are the parameters that we use. So the results, here we show the strategy prediction accuracy versus the number of training samples required. So we show here the four types of models that are shown by the four plots. The brown model, the brown plot is a random sampling where we sample instances at random. The orange plot shows the group sampling where we sample the students and problems by forming simple groups of students and problems. The red plot shows the clustered sampling approach where we use only the strategy symmetry. And the blue one is the one that we proposed in this model that uses both strategy symmetry and mastery symmetry. So as you can clearly see that our approach is the best performing model as it requires the least training samples to reach a high accuracy. And this is true for both data sets. Next, we show the accuracy versus the training time required to receive an accuracy. Here we see that a similar story where our proposed approach is the best performing model as it requires the least time to achieve a very high accuracy. Next, we show the results on fairness. For this one, we create groups based on performance. So performance relates to the fraction of steps that the student gets correct. So here we divide the students into 5 groups where they get at least 30%, like 30 to 50% steps correct, and so on. And we show the results for the 3 types of models. NS is the one that uses no symmetry. SS is the one that uses strategy symmetry. And SS plus MS is our approach that uses both symmetry. So we can clearly see that our approach that uses the strategy and mastery symmetry is fair to all the groups and is high performing as well. So for concluding this paper, the relation between mastery and strategy is very important as we use this relation to learn mastery vector embeddings and applied non-parametric clustering to get strategy invariant clusters. So sampling from those clusters greatly helped in scaling up strategy prediction, and it also exhibited a high amount of fairness in prediction to different performance groups. Thank you.